Math instructions. These instructions are quite straightforward. The math instructions, add and subtract. They are output type instructions. They are instructions that address words in memory and change the value. So they are never true or false. They just execute. And I'm demonstrating something in particular here that will make sense as we go further in the lab, and that is when you turn on input 0, you may initially expected to see that source A adds source B to itself and then stores it in source A. So you would expect it to increment by 1 every time you push the button. But what you found out instead was, as fast as you could push the button, it was incrementing by hundreds. And if you did the subtract, which subtracts 1 from N71, you saw the same behavior. It shouldn't have taken you long to realize that as long as the rung is true, it's executing the add and the subtract every single program scan. Basically, you have a scan counter. Just a little aside from what we're doing here, I'm going to set these back to 0. And I'm going to add some logic. This is how you experiment and learn. So I'm going to do a true if off, then I'm going to add a timer, and we'll make it T40. We'll take a time base of 1, a preset of 1, and then the done bit. So now we have a free running timer. What's interesting is you can't see it doing anything. Every once in a while you'll see the done light flicker right here. You might see that flicker depending on the synchronization between the video card and the computer, the driver to the controller, and screen update time and everything else. I'm going to go back and change this. I replaced the true if on input 0 for the add instruction. I replaced it with a timer timing pulse, and the timer is controlled by that input. So when I push the button, the timer timing pulse is true for 1 second, and the add instruction incremented from 0 to 3,397. If I let go of the button, I have a clear instruction that is clearing N70. So every time I push down that button, it's going to increment and count how many scans occurred during 1 second. What's interesting is it doesn't always come out the same. It comes out pretty close. Let's say that's 3,400. So let's bring up our handy dandy calculator built right into our operating system, or a free app that comes with Windows. And let's pop in 3,400. That's how many scans we're getting per second off the 1 second timer. Then you do the reciprocal to give you a fraction. Now, if you're not used to looking at exponents, this is a little tough to take. Let me show you a little trick though. You can move the decimal place over 4 places, and what that'll give you is 30294, which is a third of 1/1000th of a second. So that means that this program is scanning 3 times per thousandth of a second, or 3,000 times per second. Now, if the exponent bothers you, you can always knock a 0 off, do 340, take the reciprocal, and see you've got 0.0029. But we only did 340, so if you consider the additional 0 for 3,400, that moves the decimal place over 1 more place, so it's 0.000294. That's just a little bit aside, but here's an example of where we're using an add instruction to measure an event count. In this case, it's a scan counter. I don't see any real purpose for a scan counter. There's a zillion other ways to come up with something that'll do the same thing a lot easier than this. We don't want a scan counter, so I'm going to delete this rung, and I'm going to put this in the edit mode and bring this down to here. I meant just to drag the address. Delete this rung, and I've got one rung here that has to be fully accepted. And now we're back to our add and subtract. The next thing I had you do was to throw a couple one-shots in there. So we'll put these back in the edit mode. We go up to, and we put the focus here, one shot B3/0. Go down here and do the same thing, one shot B3/1. Select that, Control Select, accept. Now we repeat the process of pushing in the push button or turning on input 0. See, it increments by 1. As I can hold it down forever, it's only going to execute one time. So now we have the add instruction behaving identical to the counter data type, except that we don't have a done bit. Now, as we have an accumulate value that is accumulating the events of the false to true transition to the left of B3/001 shot, and then the same for decrementing. If you wanted to make this an up-down counter, we would just change this to N70. That way we're working against the same integer value. Just like the accumulate is a signed integer, so is N70. Now personally, I use one shot add subtract for my increment and decrement in almost everything that I do. I don't know how many other engineers do that. I did that because originally the counter data type, with that little nuance, if you create a new one online, that it counts once. It used to be worse than that. That's the only thing you have to worry about now, is if you create a new counter instruction, and if the rung is true, when you complete the edit, it will increment by 1. I don't need a done bit. If I want to do something on a particular count, I'm going to add another rung of logic, and I'm going to use other instructions that you've worked with. For instance, if I use the equal, then it'll only be true when it's equal to that. If I use greater than or equal to, then it will behave like the done bit, so to speak. Of course, I have to throw an output on this, and we'll just use any old bit, we don't care. And so I'm going to say N70, and by the way, I don't have to type it in, I can drag it over there. If you can see it, you can probably grab it and drag it. You're not really grabbing it, you're grabbing a copy. If these rungs were in the edit mode, then you got to be careful what you grab and drag, okay? But if I point and drag, and this is not in the edit mode, that's exactly what's going to happen. I'm going to get a copy of it. So let's say we want a preset of 10. And by the way, if I want that preset to be variable in the run mode, then what I do is I just type in an integer address. Now, right now, obviously, 4 is greater than 0. So let's put in our preset of 10. See, now it's not true and that bit is off. If I increment, see, at 9 that bit's not on. At 10 it is on. At 11 it's still on. See, that behaves just like the done bit in the counter data type. If I increment down below 10, it goes off. So there you have an up-down count logic with a bit that behaves just like the done bit of a counter. As far as the enable bit goes, I've never seen anybody use that bit. There is no counter counting bit like a timer timing bit. This is a good illustration here of how to use add and subtract. Keep in mind, if you're going to use add and subtract and you're going to put it in your logic, remember, when the rung goes true, it's going to add or subtract whatever you've got set up. If the rung stays true, it's going to re-execute the add or subtract or both every 1/3 of a thousandth of a second. That's just this particular program. So 3,000 times a second is going to execute that logic. So typically, if you want to do a math exercise, in other words, you want to calculate some value, you don't want to keep calculating it over and over again. Now, you could do that. The only reason this became a scan counter is because we put the value into a different register. In other words, N70, N70. So we're incrementing the same register. Back to our conveyor application. In the manual, I showed you 2 conveyors. And we have 2 photo eyes, and we have N70 and N71. N70 is a signed integer of the count of cartons or objects on conveyor 1, and N71 is a signed integer that has the accumulative counts of cartons or objects on conveyor 2. And then we pursued from there. The basic idea here is that when I'll turn off 1 PE there, and remember now we could go add the logic that we had before for using the trailing edge and the timer to eliminate bobble on the carton, but let's just keep it simple for right now. When 1 PE is optical path is blocked, and of course if we had bobble, then it would count too many times. So we're just going to block the photo eye, release, and now we have a carton. We have 2 counts here, N751 and N70. And let me go and add the text on these counts. 1 PE indicates that a carton has moved onto conveyor 1. So every time that the optical path of 1 PE is blocked, like right now, on the leading edge it increments or adds 1 to N751. So now we have 2 cartons. N70 is also 2 cartons. The difference is that the product count, N751, will accumulate without any interaction of conveyor 2, whereas N70 is just the cartons on N70, because when a carton leaves conveyor 1 and goes to conveyor 2, and I'm going to block the optical path of 2 PE now, and you will see that N70 decrements by 1 and N71 increments by 1. If you scan down and look, you can see this is the total count of adding conveyor 1 and conveyor 2. This is the total count. And then we are comparing the total count of N70 and N71, in other words, conveyor 1 and conveyor 2. We add those together to get a value of N752, and we compare that to the product count coming in, N751. And if that ever becomes different, then we set an audit alarm, meaning that it doesn't add up. Things didn't add up. I'm going to, in order to emphasize that, I'm going to put a couple more on conveyor 1 and put some more over onto conveyor 2. So see, now it adds up to 4, and 4 equals 4. Now let's say that someone comes along and grabs a carton off of conveyor 2. So to simulate that, I'm going to put a 2 in there. And now you see they don't add up. The product count and the total count do not reconcile, and so it sets the audit alarm. There's many ways that this could happen without somebody actually removing a carton off the conveyor, but we're not going to worry about that right now. We're just using the add and subtract instructions in a semi-practical application. The most likely reason for this to happen, and I'm going to clear these by hand so it's all zeros, and I'm going to toggle that bit off. Now let's toggle 5 onto conveyor 1. 1, 2, 3, 4, 5. Now let's toggle 6 off of conveyor 2. There's a problem here. If we add up -1 and 6, we get 5, and 5 matches. Now the way that we could have toggled 6 off of Conveyor 2 is if some long-haired leaping gnome walked by and put their hand in the photo eye when there wasn't actually a carton there. That would signify one leaving Conveyor 1 and going to Conveyor 2. So now we have to make another change to get rid of this possibility of a negative value, because there can't be a minus value carton. Okay, we added a greater than 0. The Conveyor 1 accumulate value has to be greater than 0 before you can subtract 1 off. So when I hit 2PE flagging, see, it's not subtracted any off of 0. However, it is still adding to N71, so it's adding cartons that are not there. This would be a much better solution, and that is to use the greater than 0 for both the subtract and the add function. I'm going to toggle 3 cartons onto Conveyor 1 and then 3 cartons off. Now you see they're at 0. If I go 1 more, 2 more, see, no alarm. That's because you can't toggle off more cartons off of Conveyor 2 than what you toggle on. So using this greater than instruction, and of course right now you look at that and you see that it's equal. N70, a value of 0 is equal to the constant of 0. You could put in a pointer here, but this is always going to be 0. It's always going to be used as greater than 0, so I would not waste the time making that a pointer because there's never going to be a use for it being anything other than 0. In the next piece of the lab we did multiply and divide, which are really straightforward. When I typed these, I did these online. I deleted the other rungs online, added these 2 rungs. Immediately when I finalized them, the processor faulted simply because you cannot divide by 0, period. So you see here I have divide by 0. I immediately faulted. Whenever you get a fault, always go to the error. Don't clear the fault yet. Okay, minor bit is set at the end of the scan, refer to S5 minor bits. Okay, and the S5 minor bits is math overflow trap. And that's usually had a value higher than what the signed integer can represent. So you see the result of dividing 3 by 0 is 32,767. Well, that's not the correct answer. The answer would be infinite. But it tried to calculate a value of higher than 32,767 and immediately faulted. You could clear the major error here. You see it goes back to the program mode. However, we want to put in some values before we cause the exact same problem again. Now we'll go back to the run mode, and we're good. 1 times 1 is 1, 1 divided by 1 is 1. And these math instructions are straightforward. I mean, there isn't any way you can complicate these other than you got to be really careful not to divide by 0. And an obvious way to do that is to do what we did in the last section, and that was use a compare, only this time we want a greater than. So we want N711 to be greater than 0. Now if I make this 0, see, it's not going to fault because it's not executing this division instruction against those values because this is false. N711 is not greater than 0, so this is false and it doesn't execute it. If I bump this up to 1 or 2, 1 divided by 2 is still 1, simply because these are whole numbers. They're integers. They're not fractions. If this was floating point, then we would get a different story. And just for grins, I know we didn't do this in the lab, but as long as I said it, let's throw in another division with it. And we'll throw in 1 here. Now you see this is 1 divided by 2 is 1, 1 divided by 2 is 0.5. So if we had used a floating point, we would have gotten a decimal fraction as the result. And so you can go through and play with these instructions all you want. You just have to be careful not to do certain things. Let's try multiplying by 0. Okay, it will let you do that. That's what we had to begin with. We didn't have any values in here. So it works just the way you would expect it to. You can also use one-shots to prevent a second or third execution if you want to execute it one scan and one scan only.